Thank you.
It's me, all good.
All right. So I'm very happy that we have Kevin Liu today to speak to us about moments of colored permutation statistics on conjugacy classes. But before we begin, I want to remind you of our community statement, and in particular, our three agreements that we are all learning. Everyone has something to contribute, and no one has all the answers, not even the speaker. If you have questions during the talk, feel free to interrupt the speaker or put them in the chat, and the organizers will keep a lookout on the chat so that you don't have to, Kevin. And with that, we're very excited to have Kevin Liu today.
Hi, everyone. Thanks for letting me talk at the seminar. So this is on moments of colored permutation statistics. Sorry if you don't know what colored permutations are. I actually will mostly stick with just regular permutations. Okay, so this started at GRWC in 2022. So this is maybe a slide to plug attending. It's a great time. I think I met Marge there, along with several others. And so these were the two problems we initially started on, which was looking at statistics on conjugacy classes, the symmetric group, and then looking at possibly products. But we actually never got to the second problem. We were just always on the first one, kept getting more and more questions, and we literally don't have all the answers. We might have more questions than answers, which is okay, more unanswered questions than answers. Okay, so we'll be talking about the first problem, the majority of this talk. Okay. First off, gonna go ahead and I guess overview notation. I'm actually gonna be swapping a lot between two different ways of writing permutations. So there's the two line where you write 1, 2, 3, and then the images of 1, 2, and 3 in the second line. But since the first line is always the same, you only need the second line. So this gives you the one line notation. Then there's a cycle notation where you kind of read around in circles. So on the bottom right here, the cycle 1, 3, 2, this is saying 1 goes to 3, 3 goes to 2, and then 2 wraps around and goes to 1, which is the same thing as what you see in the two line. So depending on what you're doing, one of these notations might be better. We usually see that the cycle notation is better for conjugacy classes for a reason that will come up in a moment. All right, I will mostly stick with these two statistics because they're like fairly concrete. I like to think of an inversion as any pair that's out of order after you perform the permutation. And then I like to think of descents as sort of like consecutive out of order pairs. So here's a big table. The one line notation on the left, the descents and the inversions. So for example, if you want to spot your inversions, you're essentially looking for any pairs that are out of order, and then you record the positions. So for example, in the permutation 3, 1, 2, you have 3, 1, which is positions 1 and 2 have elements out of order. And then there's the 3, 2, which are positions 1 and 3. And so you have one descent, which is positions 1 and 2, and then two inversions, 1, 2, and 1, 3. And so if you want some idea of why we care about these, the inversion statistic is measuring how elements are out of order. So if you're trying to like sort, say, a whole stack of books on a bookcase, usually you want to reduce the number of inversions. Like pairwise, you know which books come first, and you can think about, okay, to get them all in order, I need to get to 0 inversions. And if you were going to do this in sort of a naive way, you might just look at like consecutive elements or consecutive books and just swap them whenever they're in the wrong order. And this is exactly the sense. Really, the reason I'm more interested is because of you can take this group presentation, the symmetric group, using adjacent transpositions. And what happens here is in the inversion statistic tells you how many of these transpositions you need to get your element. And then descent is sort of like what could be the first or last element. And this is really the idea behind the weak Bruhat order, which I will not go into, but this is a post-it on your permutations. You can think about your sorting algorithm as trying to get to the identity element in some like fast way. Okay, that aside, let's start with maybe a small example, which is looking at just the mean of these statistics in the entire symmetric group. I'm going to go and introduce a little bit of notation, which is this thing called the expected value. So in a sort of typical notation probability, this is, for our purposes, just calculating the mean, because we're going to take like the uniform distribution or measure on symmetric group. So this E, SN, DES, and IM, this is just the mean of the descent or inversion statistic. And this ends up not being terribly difficult. What you can do is use this kind of nice involution where you just swap the images of I and J. So for example, here is S3. If you swap whatever appears in position 1 and position 3, you'll get sort of this involution. And the thing to notice is in each pair, exactly one element has the inversion 1, 3. And it's because you've sort of like literally swapped what's appearing. And sort of based on this, you can sum up your grand total number of inversions or descents over the entire symmetric group just by looking at pairs. And when you average everything out, this is sort of what you end up with. So this is sort of a nice exercise. Maybe like do it as an exercise in your undergraduate course or something. Okay. On the other hand, what we were interested in was in conjugacy classes. And first off, note that this sort of trick from earlier doesn't work in conjugacy classes. The easiest way to see this is the identity permutation. If you conjugate by anything, the identity just like doesn't change. And so it's in its own conjugacy class. It also has no inversions and no descents. So we expect some sort of like different behavior depending on the conjugacy class. And this is maybe a good time to remind you that in the symmetric group, conjugacy classes are determined by cycle type. So we record the length of the cycles that appear in the cycle notation. And the way we're going to usually index them or express them is using like a bunch of elements with a string of numbers where you have I, and then the exponent's recording the number of cycles of length I. So here's an example. You could have 3 cycles of length 1. This is the identity permutation, essentially. You could have 1 cycle of length 1, 1 cycle of length 2. So here are the 3 permutations. Or a single cycle of length 3. And then I calculated DES and IM on these permutations, and here are the means. So what you should see is that, like, okay, we get some very different behavior depending on the conjugacy class. But this is a small enough example where it's not possible to illustrate this. But what we'll see is that for a lot of conjugacy classes, things do sort of end up being the same. Okay. A lot of our work actually goes back to Fullman, who considered this for descents. So here's Fullman's result. There are 2 parts. The first is if you want the mean number of descents in a conjugacy class, here's a formula. And one interesting observation that we picked up from this was only the number of cycles of length 1 and length 2 actually matter, and n. Namely, if you like have no cycles of length 1 and no cycles of length 2, and you just like add anything possible in the remaining cycles, you still end up with the same number of same mean number of descents. And then the second thing Fullman showed sort of more generally is that when you're when you have no cycles length 1 through 2 times m, your nth moment of the descent statistic is going to be the same on C lambda and on the symmetric group. So the nth moment is just the expected value of your statistic to the nth power. Now, I don't know how much statistics and probability I've done. In case you want sort of like, why do we care about these moments? Well, they tell us a lot about distributions. The first moment's the mean, as we've seen. If you take the first and second moments, this will let you recover your variance and standard deviation, which is kind of measuring how spread out your data is. And then in some cases, moments actually determine your distribution exactly. So the normal distribution is one case. So one consequence of Fullman's result, I guess maybe I should hop back and say, okay, Fullman's result says, as your sort cycles disappear, your moments for your descent statistics start to line up on conjugacy classes in the entire symmetric group. So if you take, say, a sequence of conjugacy classes where the short cycles are disappearing, we formalize this using like the number of cycles of any length approaches 0 as n goes to infinity. Then what's going to happen is asymptotically, your descent statistic is the same on like those conjugacy classes and on the entire symmetric group. These are known central limit theorems for the descent statistic on Sn. Sorry if you didn't follow that entirely, just note that moments tell us a lot, and that's sort of the big picture. And people are like heavily interested in moments. Okay, so we thought about what happens in the inversion statistic. At least the two statistics seem close enough related that maybe we get sort of similar behavior. And I'm going to work through kind of an example to sort of convince you, okay, it should be that they have similar behavior. And the simple example involves the case where there are no cycles of length 1 and no cycles of length 2. So I think in my title here, I wrote lambda equals 1 to the 0, 2 to the 0, and then arbitrary number of other cycles. And the way we did this way back at GRWC is we thought about, okay, earlier we had this idea of looking at pairs I and J and checking for inversions. Our involution from earlier didn't work, but maybe we can still try and make it, we can try and edit that a little bit. So we looked at these inv ij indicator functions. This is just going to give us a 1 whenever we have an inversion and a 0 otherwise. And since inv can be broken up into a sum of these inv ij's, one thing to know is that this expectation function is linear. So if we can calculate the expectation of these inv ij's, we can try and get the expectation of inv. And one fact from probability is that if you want the expected value of a function that takes value 0 and 1, then it's just the same as the probability that your function takes value 1. Yeah, you can go through sort of the like, how do you calculate expected value and sort of figure this out. And so what we did was, okay, let's just look at the case where there are no cycles length 1, no cycles length 2. Can we calculate this probability? And what we ended up doing was using the law of total probability. This is where if you want to measure, say, the set A, what you can do is you can chop up your space in a bunch of pieces, intersect A with those pieces, and then measure each of those intersected pieces and add them up. And then the second part is sort of the definition of conditional probability. So if you want probability of A and B, it's probability of B times probability of A given B. So I think of this sort of like probability of A condition on omega n as look at set omega n, what's the probability that A happens? And this ends up being what we ended up picking for our partition. I guess the big idea is that when we're looking at I and J, these are distinguished elements. Everything else is maybe not that important. So we have a set omega 2 that sort of collects the cases where the permutations that send I to J. We have this set omega 3 that collects where permutations send J to I, and then omega 1 sort of capturing everything else. One thing to note here is we're already kind of seeing this no cycles length 1 or 2 being important. Namely, omega of I is never equal to I. Omega j is never equal to j because there are no 1 cycles. And then omega 2 and omega 3 don't intersect because there are no cycles of length 2. So this is sort of like, okay, we do seem to be in a reasonably simple case. It doesn't really matter what A3 through AN are. This sort of partition is like nicely defined. And so if we use the law of total probability, it seems like we just want to calculate or analyze these 6 elements in the sum. Now, it might seem like, okay, we've not actually made this any easier. We went from 1 probability to 6 of them, but actually, the situation ended up being surprisingly nice. So first off, if you want to calculate the probability that you land in one of these omega sets, it's not so bad. Omega 2 and omega 3 just have probability 1 over n minus 1. And our general approach was to use conjugation because we're in conjugacy classes. More specifically, we use this nice fact, which is that if you have permutation sigma, and it's got this cycle notation, when you conjugate by tau, what's going to happen is you're essentially evaluating, you're using tau and evaluating every element in the cycle. And why this is helpful is because if we want to know the probability that I goes to j, well, we conjugate by this element that's basically a long cycle, but you remove the element I. And so any permutation that has I and then 1 appearing in its cycle notation is going to have I2 appearing when you do this conjugation. Everything that has I2 is going to map to something that has I, comma 3, and so forth. And what this does is it decomposes your set, your conjugacy class based on the image of I. There are n minus 1 possibilities, and only one of them is j. And so this is where this probability being 1 over n minus 1 comes from. And note that when you do this conjugation, you do get bijections. And so these sets actually do have the same size as sort of like a side consequence. Okay, so you do that twice, and this tells you that omega 2 and omega 3 have the same size, which is 1 over n minus 1. And then omega 1 is kind of whatever's left over. And already you see, okay, the number of cycles length 1, number of cycles length 2, when they're 0, this is always going to be true. And so maybe the second part is also pretty nice. And I would say it wasn't like as nice as we wanted, but it gave us sort of the ideas we needed to make some more general statements. So we're gonna, I guess, like overview what happened. First off, in omega 1, I and j don't map to each other. So what's gonna happen is they're not next to each other in the cycle notation. It could be that they're in the same cycle or possibly they're in different cycles, but they're not next to each other. And when you conjugate, you're just gonna change where I and j appear. Namely, what's gonna happen is, for example, if you look in this second example, I is going to B2 and then j is going to C2. When you conjugate, you're going to make j go to B2 and I go to C2. So you're interchanging now the images of I and j in sort of the same way we did on the entire symmetric group earlier. And sort of by similar reason, what you see is that in omega 1, your probability of having inversion is 1/2. Exactly half of the elements have an inversion. I like to think of this as like the generic situation. In Sn, this was true. And this is the part of C lambda where the same thing is true. And really omega 2 and omega 3 are where things are a little funny. But even there, things aren't terrible. You can do some more conjugation again to group up by where certain elements go. So this time I've deleted I and j from a long cycle. And when you conjugate, you will group up elements based on the image of j. So in omega 2, I is always going to j. And now where's j going? That's how we're going to group up our set. And so we get n minus 2 of these sets, which all must have the same size because of this conjugation. And now you can just count out, okay, how many of these actually have an inversion, given that you know I goes to j. Here are the actual numbers. The exact calculation is not important. The main thing to note is just that we had this nice way of kind of splitting up our set into pieces of the same size. And so again, exact calculations don't matter, but you can calculate this probability for having an inversion at ij. And if you do some summing with some combinatorial tricks, you'll end up with a formula that looks like this. So hopefully I've convinced you that, okay, it's entirely reasonable that as sort of the short cycles disappear, we should get the same thing. This partition sort of like does it in a nice way. And now is maybe a good time to hop back and go back to Fullman's result. So Fullman showed that when there are no cycles of sort of short length, the nth moment on C lambda and Sn will coincide. What we just showed is that for the inversion statistic, this is what we get when there are no cycles of length 1 and 2. One thing you can check is that this is not the same thing as the expectation on Sn. So the takeaway here is we don't expect statistics to coincide, their means to coincide on C lambda and Sn in general. But one thing we can expect is possibly the moments will stabilize. And so this is, I guess, the natural next question that we thought about, which is it true that when you have no conjugacy classes of length 1 through 2, sorry, no cycles of length 1 through 2m, that your nth moment of the inversion statistic stabilizes to the same value? Not going to be the same as Sn probably. It shouldn't be, but maybe it's stable. I guess maybe I should stop for a moment here. Questions and okay, so when we thought about this question, we decided maybe we don't want to do what we were doing earlier, trying to figure out what sort of goes into m to the nth power, and trying to pick a nice partition was too complicated. And so we took sort of a slightly different route. The main idea we extracted was if you do some nice conjugation, you can group up by the images of various elements. So we thought, okay, can we use this property for more general permutation statistics? And this is exactly what we did. So I'm going to take a moment and sort of like step out and look more globally. So a permutation statistic is just going to be any function from S and R. We looked at sort of based on this idea of grouping by images of various elements, we looked at this thing called a constraint. And so what this constraint does is it's just going to give us a bunch of ordered pairs of elements in N. And where you looked at these indicator functions, which I'm denoting I sub k. And this is just going to give me one on permutations that satisfy sort of what's given in these ordered pairs. You can think of these ordered pairs as a function. And this indicator function is just saying, does my permutation restrict to these pairs as a function? And one thing we showed is that if your constraint K, capital K, has little k elements, then on conjugacy classes where you have no cycles of length 1 through k, your expectation stabilizes. It's either going to be 0 or it's going to be this like 1 over, I guess this is like n permute k elements. And in particular, you get something that's independent of lambda.
I just wanted to make sure I understood constraints briefly. So constraints are saying I'm going to send 2 to 5.
That's
like
correct.
in my permutation. They're not inversions or anything like that.
No, they're not inversions. Yes,
Okay.
You're correct. So, for example, you could send 2 to 5 and 3 to 1 and so forth. You could also think of them as partial permutations. So you're going to send some subset of the elements to other elements. Thank you. And so the big picture here is like the probability that you satisfy a constraint, which is what this expectation is really telling you. It's either going to be 0 or this nice fraction when you have those cycles of short length. And our general way of proving it was sort of like using our idea from the inversions. Okay, first off, the 0 case corresponds to certain kind of impossible situations. Like we really want this k to be a partial permutation so that like you don't want 1 going to 2 and 1 going to 3 also. That doesn't really make sense in terms of permutations. So whenever this happens, you're going to get expectation 0. And really, we should kind of omit these. In the definition, we didn't omit through this possibility, but in general, we're not interested in them. There's also a second case, which is it's possible that when you say, okay, certain elements go to other elements, you might force yourself into a cycle. So for example, if 1 goes to 2 and 2 goes to 3 and 3 goes to 1, you've got a cycle length 3. And so when you know that your conjugacy class has no cycles of length little k, this is sort of like impossible, given that your, sorry, maybe I should back up a second. It's possible that these little k conditions in here imply a cycle of some length, and that cycle length is going to be at most little k. You can think about like literally forming a cycle using the constraints, and it's going to have at most little k elements. And we assume C lambda does not have any of these short cycles. And then in the other case, we use our idea from earlier. You can do this nice conjugation to find that there's a 1 over n minus 1 probability that any element I1 goes to J1. And then you work through some sort of technical details on induction to try and get the other part. The inductions may be easiest to see on the long cycles. So if you have a single cycle of length n, then you're really just trying to line up sort of this certain substrings. Where the technical details comes in is like you have possibly many cycles. Some of them share the same length, some of them are different lengths. Certain elements are appearing inside or not in the same cycle. And so there's a little bit of like work to do there, but it can be like worked out in a reasonably nice way. This also motivated, I guess, 2 definitions. One of them is this notion of well-definedness. So we want all these IHs and JHs to be distinct. This way we get like an actual partial permutation. And then we also introduce this notion of acyclic, which is basically saying that if you satisfy the underlying conditions, you don't have to have a cycle. Best illustrated with examples maybe. So the first one's not well-defined since 1 is going to 2 different elements. The second one is well-defined, but we do have this cycle of 1 going to 2, 2 going to 3, 3 going to 1. So any permutation satisfying K2 is going to have that 3 cycle. and then K3 is actually acyclic. Okay, so I've done all this, and you might wonder, why did we, think about this world? And more or less, what we're trying to do is we're trying to like take these indicator functions and think about linear combinations of them. So we're going to say a statistic is realizable over a constrained set of size k. We can express x as one of these linear combinations, where each of these capital K's have at most little k element. And maybe this is best illustrated with an example. So the inversion statistic from earlier, if you were going to try and do it in a naive way, maybe not trying to be very efficient, you're just like, how do I check for inversions? One thing you can do is you can look at every pair I and j. You can look at every possible image, like for omega of I, omega of j, which we're going to call k and l. And you're going to check, does I go to L and j go to k? Whenever this is true, record a 1. And then check this over all I, j's, k's, and l's. And this will give you like a decomposition of IMV into these indicator functions. And the thing to note is these indicator functions have 2 pairs in them. So in this case, you can think of it as little k's too. Okay, questions on this example? Make sure we see. Because we just went through 2 or 3 slides of like, these are constraints, and this is sort of the like, why would you want these constraints? And mainly the reason we want these constraints is because the linearity of expectation is really nice. So give a shot back. IMV is given by this sum. If you want the expected value of IMV, the expectation function is linear. So you can think about the expected value of each of these indicator functions. And from earlier, we know that when there are no cycles linked 1 or 2, this expectation is either 0 or it's going to be 1 over n minus 1, n minus 2. So you only have 2 cases. And the second case corresponds to acyclic conditions. So how many I, j, k, l selections do I have that don't give me a cycle? Note that whenever there is a cycle, it's going to have length 1 or 2. And so if you count these out, you can get our earlier formula for IMV. And it also shows that, I guess, this demonstrates a much more general fact, which is that when you have a statistic realizable over some constrained set of size little k, your expected value on C lambda is going to be the same when there are no cycles of length 1 through k. And the proof goes exactly like the inversion case. You start with this decomposition as a linear combination, take the expected value, and then argue, okay, I'm going to pick up a bunch of zeros, and then the only non-zero terms are the acyclic conditions. And this sort of like acyclicity doesn't depend on the conjugacy class. And I guess as a remark, really what we show is this. Your sort of weights showing up, and then this sort of like 1 over n minus 1 through n minus the size of capital K in the denominator. And if you wanted to, like we did with the inversions, you could explicitly calculate some expected values. We're not going to do that. Just want to know here that sometimes you get some fairly nice formulas. Other times you can show these are polynomials. You'll always get something kind of rational, but polynomial is sort of a nice special case. And so at this point, we know, okay, like the mean of the inversion statistic when there are no cycles linked 1 and 2, we expect this mean to stabilize. And actually, with the notion of constraints, this gives you a very easy way to translate to higher moments. Essentially, what happens here is if you want the product of 2 of these indicator functions, it's the same thing as unioning their constraints. The way I think of this is the only way the left side is going to give you 1 is on permutations where K1 and K2 are both satisfied. And that's the same thing as like satisfying K1 union K2. And what you can do with this is if X is given by this linear combination, you can look at X to the m power. You can express that as this sum to the nth power, and then use the distributive property a bunch. And what this does, after you union up constraints, is if X is realizable over a constraint set of size little k, then its mth power is realizable over a constraint set of size m times k. And so the earlier theorem really tells us that if you have something realizable over a constraint set of size k, then the mth moment is going to stabilize when you have no cycles of length 1 through m times k. And so this is sort of that inversion statement from earlier, generalized now, where in that case, K was 2. And we thought, okay, this was a much nicer way of going about it than trying to keep doing these like decompositions into those omega sets. But very much those omega sets like motivated what we ended up doing. Okay, so we thought this was really cool.
Small question.
Sure.
So does realizable over a set of size K have like a minimum condition?
So
when you say it's realizable set a size K, is it minimum K or
it doesn't have to be minimum K.
Okay.
The result will hold without K being minimum. For the full strength of the results, you do want K to be minimum.
Okay.
Like you want to minimize it. One thing we sort of encountered, and I guess this is one of those like questions that opened up from doing this, was if you took a statistic and you try to minimize this K parameter, in general, it seems very hard. In versions, at least, it was like, oh, it's like K equals 2 is already a very fast bound that you can get. But for other statistics, it seems like things are maybe a little harder to do. For example, if you were trying to say like longest increasing subsequence or something like this, I don't think we have any idea how to go about that as far as like minimizing this K parameter.
Okay.
But there are a lot of statistics where this was really nice. Like for example, exceedances and permutation pattern statistics are still fairly nice. I guess that was a long-winded way of saying K doesn't have to be minimum, but ideally we would want it to be. Okay, we thought this was cool. Oh, question?
Sorry, a question also on Ks. Does it pose a problem that here maybe K1, K2 have common elements? So is it constrained sets of size maximum MK a problem, or?
So we in our definition managed to sort of like define that problem out. More or less, like when we say realizable over a constrained set of size K, this says that each of these capital Ks is less than or has size less than or equal to little k. It doesn't have to be that all these capital Ks are exactly size little k. Does that make sense?
Yeah, thank you.
That was mostly out of convenience. Also, you can show that anything realizable over, or like any one of these capital Ks, if it doesn't have size little k, you could just try and throw in more conditions to like break up the sum. Like for example, if you have capital K is just 1 goes to 2, you can break up I sub capital K into a sum of other constraints by just saying, okay, sum over all possibilities for 2. Like do a sum over all I of 1 goes to 2, 2 goes to I or something. And you can sort of like arbitrarily increase this sort of size parameter. Okay, so this is about what we did at GRWC, and we thought this was really cool. One sort of unfortunate thing that happened is that we found out actually right before GRWC, someone had posted something on Archive that had some sort of like similar flavor of ideas. So these two people were Zach Hamaker and Brendan Rhodes. Zach is at Florida and Brendan is at UC San Diego. So, well, we have conjugacy classes. You might think, okay, maybe there's some representation theory, and there is some representation theory is the short answer, which I will try and summarize briefly. This in no way encompasses what they did, like accurately or in complete picture. But you can think about this expectation in a slightly different formulation. So when you have a statistic X, you can think about, okay, I can average X over all conjugations in the symmetric group. This is sort of a very common idea in rep theory, which is like, essentially what this does is it is now going to take every element and map it to the expected value of your function in the conjugacy class containing that element. And here's maybe some details, not super important. The main thing is that we sort of like average over conjugacy classes doing this X bar statistic. And so what you see is this X bar is going to give you the same value on all elements in the same conjugacy class. And we call these like class functions. And one fact from representation theory is that your class functions, you can get a basis for these class functions using your irreducible characters. So this is take your irreducible representations and then take their traces. One thing you might ask is, okay, what if you take this X bar and expand it in terms of irreducible characters? One fact from rep theory that I will not go into, but it's good to know for sort of their results, is that these irreducible characters are also indexed by partitions. And if you have this partition where the largest element has size n minus k, then the character for this partition is actually going to be a polynomial in n, and the sort of short cycles being the ones of like length 1 through little k. What Brendan and Zach showed was that if you have something realizable over a constraint set of size k, then X bar, when you expand it in terms of these irreducible characters, you only need the characters for partitions where the first part is at least size n minus k. Your biggest piece is at least n minus k. And what ends up happening is if you use sort of this fact from above, you'll get that X bar as a class function only depends on n and then these a1 through ak parameters. And so namely, if you plug in 0 for a1 through ak, which is capturing the no short cycles idea, you should get kind of the same function. So this unfortunately posted up right before we started work. So that was unfortunate, but I mean, the upshot was this made us think about something that we were going to do anyway, which was like what happens in other cases. I don't know if y'all are aware of this type B or type D question. This is sort of a natural thing that comes up at some point if you do combinatorics long enough. I think everyone asks this question in every talk. So I've now asked it, and so that's taken away from you all. I'm sorry. If you don't know what these are, that's fine. We actually don't need them, because what ended up happening was we looked at type B and realized, oh, the situation here is actually really nice, and we can go further. And this is what leads us to colored permutations. So if you want the sort of like terse definition, this is a Reef product. It might be that this means absolutely nothing to you, and that's perfectly fine. The definition that's actually going to be helpful, I think, is you can think of it as you take R copies of the elements in 1 through n, and you're going to color them using an element in Z mod R. And we're looking at the permutations that satisfy whenever I colored 0 goes to J colored C, you can shift up this color, and it will shift up in the image as well, where everything is taken modulo R. And just to sort of see the special cases of this, the regular symmetric group is R equals 1. Like, there's only one color and nothing particularly interesting happens. And then R equals 2 is the sign symmetric group. You have 2 colors, which you can think of as like positive and negative. The way I like to think of this is like you've got several copies of the same elements. Here I've literally colored them different colors. And once you specify where the elements colored 0 go, it sort of determines everything else. So if 1 colored 0 goes to 4 colored 1, then 4 colored 1 goes to, 1 colored 1 goes to 4 colored 2, 1 colored 2 goes to 4 colored 3. Also, if you knew like 1 colored 2 goes to 4 colored 3, you can recover the fact that 1 colored 0 has to go to 4 colored 1. So there's sort of like nice regularity pattern. I'm not going to draw everything else in because it would get really chaotic, but this was sort of like how I picture it in my head. It's sort of you're wrapping around on a cylinder with this nice sort of like parallel property. And what we found is that actually the conjugacy classes aren't so bad. First off, you have the same kind of cycle notation. I shouldn't say same. It's actually a little bit funny. Essentially what you do is you only look at the elements colored 0, look at their images, and then you try and form cycle notation in using just those elements. It was a little unnatural at first. So like in the cycle notation, you should not interpret this as 1 colored 3 goes to 4 colored 1. We only have the images of elements colored 0. You should interpret this as 1 colored 0 goes to 4 colored 1. 4 colored 0 goes to 3 colored 1, and so forth. And the reason you would use this convention is because you can define the color of a cycle, which is you add up the colors that appear, and then conjugacy classes are given by colored cycle type in this case. So for example, up here we have a length 3 cycle of color 5, which is the same thing as 1 mod 4, and then a length 2 cycle of color 4, which is the same thing as 0 mod 4. And using sort of like this convention, you can describe the conjugacy classes fairly well. Specific details aren't that important. The main thing is that note that we still have this sort of cycle notation, and now every cycle has a color. And colored cycles now give us our conjugacy classes. So we sort of define this natural generalization called a color constraint. Now we have like little k elements from sort of like the colored elements, where we go ahead and assume that, okay, maybe the first coordinate, we always have elements colored 0. If you don't, you can always sort of like shift using the nice regularity property. We define these indicator functions again. We did this sort of the same notion of realizable over constraint set. This is essentially the same definition with Sn replaced by Snr. And we generalize our earlier lemma, which is that if you have one of these color constraints of size little k, you either are going to have that the expected value is 0 on conjugacy classes with no short cycles, or it's going to be this value. The main new addition is 1 over r to the k term. So in the symmetric group, which is r equals 1, you don't see this term because r is 1 and 1 over 1 to the k is just 1. So this does sort of specialize properly. And the proof sort of like was very similar. Like 0 happens because of you could have constraints that are not well defined, or maybe they force you to have a cycle of short length. And in the second case, what ends up happening is you try and think about, okay, if I want to get a color permutation, I think about generating a permutation and then trying to like color elements in an appropriate way. And this is exactly what the two terms are doing. The first term is like drop all the colors, you have an uncolored constraint. What's the probability that you sort of satisfy those constraints in the uncolored case, which is something you can do just by directly adapting what we did earlier. And then the second term is like, okay, if I generate these colors randomly on the images of like I to the 0, what's the probability that I get the right colors? And for each one is 1 over r. And so you just pick up this 1 over r k times. And then sort of the main theorem just generalized nicely, which is that if you have something realizable over a constraint set of size k, then its nth power, the nth moment, is going to stabilize once you have no cycles of these short length. One thing we also found is that interesting was that the converse does not hold. I guess we never really expected it to, but you can't exactly use this in sort of like the backwards direction. It's possible your moment stabilize on when you have no cycles of like short length and you aren't realizable over that like k parameter. Okay, I guess I flew through that a little quickly. Questions on this? Okay, I guess to wrap up, it's maybe good to go back to Fullman one more time. So Fullman had that when you have none of these short cycles, the nth moment of descent starts to stabilize, or I guess it's the same on C lambda and Sn. What we have now is we've generalized this to sort of any statistic in that you can give it this sort of like size k idea, and its nth moment will stabilize. We don't expect it to be the same as on the entire symmetric group, as far as like the expectation on C lambda. And we've not only sort of generalized this to any statistic on Sn, we've gone to sort of the other direction of colored permutation groups where we've introduced this parameter R. So there's kind of two different directions this generalized. One interesting thing is that the sense actually exhibits this behavior of being the same. And one thing we found is actually in the colored permutation case, the same thing ends up also happening, making the sense seemingly like very special. Maybe first I should tell you what the sets look like in the colored permutation groups. Essentially what you do is you order your elements You're grouped by color. Within the same color, you just use the usual order on the integers. And then your color is sort of telling you what's bigger whenever you're comparing elements of different colors. Just to make explaining this easy, we just use the convention here that an element fixes like all the capital N's once the capital N is bigger than little n. Here's an example. So in this case, 4 colored 1 is smaller than 5 colored 3, so there's no descent at position 1. 5 colored 3 is bigger than 1 colored 3, so there is a descent in position 2. And then you can kind of keep going. One funny thing is you can get a descent at position 5, even though this is in S5, 4. So this is permutations on like 4 copies of the elements 1 through 5. And the reason for this is we're gonna use this convention that omega of 6 colored 0 is 6 colored 0, and then 2 colored 1 is bigger than 6 colored 0. And so our theorem is that, okay, for this general descent statistic in the colored permutation group, it is actually true that when you have none of these short cycles, the nth moments line up on C lambda and the entire group. And using sort of the same reasoning as Fullman, this will give you this sort of central limit theorem when the short cycles disappear. And so one nice thing here is it also recovers Fullman's result for the sense, because one thing you can check is that that earlier definition for the sense just like reduces in the case of the symmetric group to the usual descent statistic. Okay, and so this is essentially what we've done so far. Some future directions is we're still looking at other statistics where this sort of nice thing happens where the moments line up on C lambda and the entire group. We've got at least one, but it's sort of like, it's really hard to tell when this will happen, and it's something that we want to explore a little more. The next note is, after this whole like Hamburger and Rhodes, their result in SN sort of encompassing large portions of what we did. Well, we looked through now, and it's very clear that people don't know similar things on the colored permutation groups yet. I mean, they had just done their work last year. And so it'd be interesting to sort of get an analog of their results. Like think about irreducible characters in colored permutation groups and expanding this sort of like X bar in terms of that. We conjecture sort of like the natural generalization holds, but we don't immediately know how to show it, but we plan to try it. And then I guess the last problem is thinking about type D. No, this is just ignore it, but yeah, that's sort of like one thing that would be interesting, because it's kind of a special subgroup of type B, and subgroups don't always behave nicely as far as conjugacy classes go. So it seems like there's some work to sort of go from type B to type D. Okay. First, I'd like to thank GOCC for supporting the project. Also, if you haven't been yet, you should go. And then Zach and Brendan for discussions on our work. And yeah, here's the preprint if you're interested.
All right, thank you. Let's everyone thank our speaker. Are there questions for Kevin? Vishal, go ahead.
Hi, very nice talk. So I guess I have the sort of maybe one of the obvious questions, which is, do you think there is any hope of obtaining an exact expression for the expectation? For example, in the case of descents, you started by showing Pullman's result, that if you have the A1 and A2, then you have a formula for it. But then is there any hope of, for example, finding something like a moment generating function, for example?
That's a great question. I am not sure. I've thought about this some. Like, I would love if we could derive this expression exactly. And our method for showing this gives us sort of some way of doing it. The problem is the way we have of doing it involves sort of this big sum. And so we would need some nice combinatorial things to happen to make the summation simplify. And so I'd say, I guess that's an area of ongoing work. Not sure yet. It would be nice if this did happen though. I will say with the Hammaker-Rhodes sort of irreducible character approach, there is some combinatorial description of how to get like the coefficients in the irreducible character expansion, but it's sort of a very complicated description that in general might be too hard to actually like calculate. Like you have to count all these things that are very complicated. So I think in both scenarios, there is some hope, but it's not immediate.
Thank you. Can I ask one more question?
Sure. I guess
Yeah.
I'm not the organizer.
So the other question is, you can refine the descent statistics into peaks and double descents. So in descent you compare sigma I with sigma I minus 1, but then you can compare sigma I with sigma I minus 1 and sigma I plus 1. And then so you have two different kinds of descents. You can have a peak, so you go up and then you come down, or you can have a double descent. Valley and a double descent. And so I guess maybe that these two might be like sort of statistics you can look at. So then you can get some sort of, because these statistics add up to count the number of descents, I guess, if I'm not messing this up.
That's interesting. I think we did come across those statistics, and I guess one thing is you can realize them using constraint sets of size 3 for sure. Possible you can do better. We haven't really thought about relating them sort of a nice way. Like maybe something like this theorem in Sn holds for peaks or valleys. You have to think about that. I guess we have not looked at them beyond the fact that they are realizable over constraint sets of size 3.
Thank you.
Other questions for Kevin? Right. If not, let's thank Kevin one more time.